As we start chapter 11, we're getting into a couple more theories, or a few more technically. So, chapter 10, we covered Lewis structures. Lewis structures are a way for us to describe how a molecule is connected in 2D space. But what students kind of get hung up on is that Lewis structures are a theory. We are trying to describe a physical world. So three other theories we have when it concerns bonding is looking at their molecular shapes, meaning their shapes in 3D space. Valence bond theory, and molecular orbital theory. Now, these theories have, of course, been developed and studied repeatedly throughout systems, so we can describe when they work, when they don't, why they were developed, etc., and we'll get into that in this chapter. But I do need you to understand that they are theories. We are using them to describe the world, and the world around us, the physical world around us, but they are still theories. So for the chapter focus for chapter 11, we have 3 different things we're focusing on. We've got VSEPR, valence bond theory, and molecular orbital theory. Under VSEPR is used to determine the 3D shape of a molecule. So we're going to draw it in 2D space because we're drawing it on paper, but we're going to try to describe it in 3D space. How does this molecule actually look in 3D space? To do this, you need to be able to determine areas of electron density and use this to determine your overall molecular geometry. I want you to ask yourself, is the octet rule obeyed? Is formal charge minimized? Are multiple bonds required? Now, there are exceptions to the octet rule. It doesn't have to be obeyed. Formal charge isn't always able to be minimized, and double bonds are not always required. But these concepts that we learned in the last chapter apply here as well. We have 5 basic geometries. Do you know your 5 basic geometries? And then if there's lone pairs on one of those basic geometries, can you go ahead and apply those as well? What geometries occur due to those lone pairs? Can you determine if a molecule is polar? So in the last chapter, we talked about polar molecules. A polar molecule is created due to a difference in electronegativity values between 2 different atoms that are bonded together. So one atom is more electronegative, meaning that it pulls more of that electron density towards itself. It's an unequal sharing of the electrons. An unequal sharing of the electrons within the bond holding them together. That is a polar bond. We must have polar bonds to create a polar molecule. That does not mean that just because a bond is polar, that the molecule is polar. Now, in order to have a polar molecule, we have to have polar bonds. So, polar molecule requires polar bonds, but polar bonds does not guarantee the molecule will be polar. It depends on the 3D shape of the molecule, 3D orientation in space. In valence bond theory, we're going to talk about hybridization in degenerate orbitals. It's basically some fancy math that we do. We don't have to do the fancy math. We just have to use the outcome of the fancy math, but some fancy math to describe the way we see bonding in the real world. You're going to draw hybridized orbitals and recognize hybridization types. We're going to talk about bond rotation, strength, and length of bonds. In the last chapter, I told you that single bonds are longer and weaker than a double bond. Double bonds are longer and weaker than triple bonds. So why are triple bonds the shortest and strongest? Why are double bonds shorter and stronger than a single bond? Hybridization in valence bond theory will help us understand this. And molecular orbital theory. Molecular orbital theory deals with a linear combination of atomic orbitals. In chapter 9, we talked about atomic orbitals, and that's when I drew things like, I would say your energy scale is going up, and I would say you're filling in your electrons, your 2s, your 2p, your 3s, your 3p, etc. And I put electrons in. That is an atomic orbital. A linear combination of atomic orbitals is used if I combine 2 atomic orbitals for an overall molecule. How do they combine to form a molecular orbital instead of just an atomic orbital? HOMO and LUMO. HOMO, we'll see this again, but HOMO stands for highest occupied molecular orbital. So what's the highest level? Is it here? Like, is it the 3p's? What's the highest level that I have an electron residing in? This should say S here. Maybe it's a 3s. Your LUMO is your lowest unoccupied molecular orbital. If our HOMO was the 3s, then the 3p would be our LUMO, the lowest unoccupied. Diamagnetic and paramagnetic, we've learned those terms before. They are back. And then delocalized molecular orbitals. Now, I do have the objectives broken down in your PowerPoint a little bit different than this video, just because I haven't had a chance to break them all apart, and I have the file saved on my laptop, and I'm doing this on my iPad. So go ahead and read through the objectives for your specific module that you're watching the video for, and at some point, maybe I'll get these synced up correctly. Okay, shapes of molecules. What are the overall shapes of the molecules? Well, these are some of the shapes we can see. There is a PhET simulation, PhET, that I will link in your online learning program that I highly recommend you go play with. The PhET simulation is phenomenal. You can put in there the molecule you're looking for, or you can put in there a combination of bonds and lone pairs, and it will actually let you rotate these molecules in 3D space so that you can better see what they actually look like, and I think it will help you a lot as you're trying to identify these things. But let's just talk about a few of these. This is CO2. CO2 is a linear compound. I've got your carbon in the center and 2 oxygens bonded to it, double bonded. And this is called this is called linear, but your outer atoms here are 180 degrees apart. This is actually SO2, and it's called bent. And the angle here is less than 120 degrees. Oops, sorry. Trying to write it that way. Trying to think about less than and more than. Less than 180 degrees here. This is water, H2O. This is also known as a bent structure. And the angle here is less than 109.5 degrees. Where am I getting these numbers from? I will show you that on another slide. This represents BCl3, and it's known as a trigonal planar. Note we've got a triangle shape, and I know it's hard to see in the picture here, but this is planar. There's a plane that I can cut through all of these atoms, and if you use the PhET simulation, you'll be able to see that plane a little bit better. But the angle's here, 120 degrees. This is ICl3. This is called T-shaped. T-shaped comes about, there's a couple different ways we can get T-shaped. This one comes about because there was actually a lone pair here and a lone pair here as well. These angles, this angle to this angle is 180 degrees. We don't usually draw lone pairs on the bonds themselves though. And then this is actually ammonia, NH3. This is called trigonal pyramidal. And the bond angles are less than 109.5 degrees. But we've got a triangular shape, and it's forming a pyramid to that triangular shape. Hence the word trigonal pyramidal. So VSEPR. I know I keep saying this word VSEPR. What the heck is VSEPR? VSEPR stands for valence shell electron pair repulsion. So we say VSEPR because it's faster, but the main idea behind VSEPR is that electron pairs are mutually repulsive. So electron pairs will repel each other. If I have either lone pairs or bonds on a molecule, they will repel each other. Electrons are going to repel each other, right? So what's going to happen is whether it be a lone pair or bond, they're going to, the molecule, how do I say this? They're called areas of electron density, and we'll see that in a sec on the bonds. But let me just write one out. So oxygen is bonded to 2 hydrogen atoms and has 2 lone pairs. This, and this are all areas of electron density. Meaning areas that electron clouds or the electron itself resides. Those areas will repel each other. And what they do is they automatically orient themselves so they can be as far apart as possible to minimize that repulsion. So molecular structure, we can follow this kind of rule. So electron configuration of atoms, we covered this in chapter 9. We apply the octet rule when appropriate. And then we get our Lewis dot structures, either Lewis electron dot structure or Lewis structures for molecules. We then apply VSEPR theory, and we can get the 3D shape of the molecule. So what does it actually look like in 3D space? From there, we can do 2 things. We can run down the side of electronegativity and bond polarity, which will be a different module. We'll cover that. We can look and see the electronegativity difference between the atoms themselves, see if the bonds are polar, and if the bond is polar, is the molecule polar? From there, we can start looking at your intermolecular forces and bulk properties. Intermolecular forces are the forces that hold the molecules together. Like, if I look at the periodic table, I know I've told you guys this before, but F2 is a gas at room temperature. Cl2 is a gas, but Br2 is a liquid, and I2 is a solid. Why? I mean, yes, I2 has a larger molar mass, but that's not exactly what's happening here. It may have a larger molar mass, but why is water a liquid at room temperature? Water's molar mass is really low. Oxygen is 16, 2 hydrogens, it's got 18.02 grams per mole. 1 fluorine atom is 19 grams per mole, which means F2 is about 38 grams per mole. But it's a gas at room temperature, and water is not. Why? We could also go the other way, go down the side with valence bond theory, and talk about the bonding description of the molecule, and then go to chemical reactivity. VBT is used a lot in organic chemistry because you're looking at bonding and reactivity for the entire semester. So how are we going to apply VSEPR? First thing I want you to do is draw your Lewis structure. Draw the Lewis structure for the molecular ion you're looking at. Each bond, whether it be single, double, or triple, counts as 1 VSEPR pair, or 1 electron group. Again, I don't care if it's a single bond, double bond, or triple bond. It counts as 1 area of electron density. One area, one area, one area. Each lone or non-bonding pair, so something has a lone pair, like water has, each one counts as 1 VSEPR pair or 1 electron group. So 1, 2. With this, you're going to determine your overall shape, allowing for maximum separation of electron pairs and bonds in order to minimize your repulsion. Name your molecular geometry based on the position of atoms, not position of electron groups. We have 2 different types. We have what we call your electron geometry, and we use this to find your molecular geometry. Two additional points. Lone pairs are more repulsive than bonded pairs, so it will actually make the bond angles between the other atoms closer together. Hence why when I went back on this slide up here, I said less than 120, less than 109, less than 109, because they had lone pairs repelling them. Now, this has lone pairs, but they're in a different angle per se. They're slightly off of 180 degrees, but not by much here. Multiple bonds usually require more space than single bonds. So here is where we're going to cover our five basic geometries. What I want you to write down in your notes is number of electron dense areas, and electron pair geometry. And we'll see this on the next few slides too. You see it right here too. We've got it written right here. But sometimes it's helpful to have it write it out on your own as well. If I have two areas of electron density, this is like saying I've got X bonded to, let's just say A and A. I don't know what those are. They're random atoms. But here I have 1, 2 areas of electron density. This is called a linear structure. No lone pairs, it's just linear. Now, if you had something with lone pairs, like say you had XC or HCl, that is linear as well. That's not going to do anything. What if I have 3 areas of electron density? It's like you have X in the center, bonded to A, bonded to A, bonded to A. 1, 2, 3 areas of electron density. This is called trigonal planar. Hence the name. Now, if one of those areas was a lone pair of electrons, excuse me, I still have 3 areas of electron density, but the thing is we don't actually usually draw the lone pairs here, so what it looks like is this in structure. We call this bent. It's not one of your 5 basic geometries, so you don't have to write this down right now, but I'm just saying this is how we get it. We get that lone pair right there. What's important right now is getting these 5 basic geometries down. If you have 4 areas of electron density, we call this a wedge. A wedge means it's coming out of the board at you. This is a dash, and we say the dash is behind board, away from you. But this has 1, 2, 3, 4 areas of electron density, and we call this tetrahedral. Because I always forget to specify this part, the bond angle here is 180 degrees. The bond angle here is 120 degrees. The bond angles here, 109.5 degrees. So notice tetrahedral, 4 areas of electron density. If I have 1 lone pair, it becomes trigonal pyramidal. And if I have 2 lone pairs, it becomes bent. We will practice more with those. If I have 5 areas of electron density, one, 2, I'm going to draw these in a different color for a specific reason. 3, 4, and 5. So 1, 2, 3, 4, 5 areas of electron density. Now these blue ones are called your equatorial. They are 120 degrees away from each other. And they're 90 degrees from what we call your axial positions. Your axial are 180 degrees apart from each other. One thing you have to note here, and you have to do correctly, if you have lone pairs, they will occupy equatorial positions. And lastly, I'm going to draw it up here for space. If you have 6 areas of electron density, we call this octahedral. One, 2, 3, 4, 5, and 6. Now, I forgot to name number 5 for you. I'm sorry. Trigonal bipyramidal. Trigonal bipyramidal specifically because we've got the triangular shape here. So the trigonal portion. That triangle is forming a pyramid to the top and a pyramid to the bottom. So 2 pyramids with a triangle in between. Again, these are easier to see with the simulation. One lone pair creates this is calling it a sawhorse. Most of us call this seesaw. T-shaped is 2 lone pairs, linear for 3. Octahedral, if it loses 1, it becomes square pyramidal. Square planar, if it loses 2, or if it has 2 lone pairs, 3 lone pairs is T-shaped, and 4 lone pairs is linear. And we will work more examples with that. But you need to get these 5 base geometries down, meaning this, your electron pair geometry, because if you can get that down, it will help you a lot as you master your actual molecular geometry. This is a nice table out of your book, so table 11.1. I highly recommend you go print a copy of this. It's got a lot of information for you, a lot of good information. Number of electron groups, number of bonding groups, number of lone pairs, electron geometry, molecular geometry, approximate bond angles, an example, compound, and what the structure will look like in space. This table, you need to know these terms, and you need to know the bond angles. So you can either memorize every single line of it, or what I have memorized is these things. And then I just kind of know what they look like from there because I look at the structures and I know what structures mean. Whatever you do, you got to get this stuff down, okay? I know it's a lot. The more practice you do, the easier it'll become to see them and see why they're named the way they are. So, some more examples. These are basically just showing what we've just done, what was in the table. They're not different structures. They're the same we've already seen. They're just ones out of your book that show a little bit better graphic, a little bit bigger. So, going through these again. Linear. Here we have 2 areas of electron density, or 2 electron-rich regions. They're 180 degrees apart. Trigonal planar, 3 electron regions, 120 degrees apart. If we have 3 electron regions, but one of them is a lone pair, it becomes a bent structure. If we have 4 electron regions, no lone pairs, we call this tetrahedral. This is where that wedge and dash comes in, by the way. This is where I would say like X, A, let's be A, X, A, and then I would say dash. This is my dash. It's coming out of the board at me. This is my wedge going behind the board. If I have 4 electron regions, but one of them is the lone pair, we call this, it's actually called trigonal pyramidal. This picture actually from your textbook, but I don't want you to just call it pyramidal because we also have square pyramids. We also have trigonal bipyramidal, and I don't want you to get them mixed up. I want this called trigonal pyramidal, that's what will get you full credit. If you have 4 electron regions, but 2 of them are lone pairs, that's what water does. That's called bent. 5 electron regions, trigonal bipyramidal. And again, I know I mentioned this in the previous slide, but we have equatorial positions and axial positions. So you've got to know the equatorial are what's forming your equator here. The triangle in the center is your equatorial positions. Your equatorial positions are 120 degrees apart from each other. Your axial positions are the top and the bottom, and these are 180 degrees apart. And then axial to equatorial is 90 degrees apart. If we have 5 electron regions, but one of them is a lone pair, we form your seesaw. Now, this may look sideways to you. Excuse me. That's because I put it sideways, because I see the seesaw better this way. You put your little person here, put your little person here, and you get to play at the park, right? It's a seesaw. If I have 5 electron regions but 2 lone pairs, we call this T-shaped. And I know it's down here, but if I have 5 electron regions and 3 lone pairs, it's called linear. If I have 6 electron regions, this is our octahedral, and every piece is 90 degrees away from each other. 6 electron regions and 1 lone pair is called square pyramidal. So this one, I highly recommend using the simulation to see, but you've got a square here. The square is forming a pyramid with that top atom. 6 electron regions, but 2 of them are lone pair, forms square planar. This is forming a square, but it's actually a planar square. I can cut a plane right through it. And then I don't have them shown here, but they look the same. This also looks, if I have 6 electron regions, but 3 lone pairs, it will give you T-shaped. And if I have 6 electron regions, 4 lone pairs, it will give you linear. So let's go ahead and work a couple examples. CH4. Now, you do start these by writing out their Lewis structure. You can, if you know how to do these without writing out the full gamut of stuff, great. If you have to take your time, that's fine, but make sure you're practicing so you can start to do them faster. CH4 has 8 valence electrons. So there's a carbon singly bonded to 4 hydrogens. If I look at this, I've got 1, 2, 3, 4 areas of electron density. And I've got, within that, I've got 4 bonds, 0 lone pair. Now, that 4 areas of electron density, this tells me tetrahedral. So your electron geometry is based on how many areas of electron density you have. Doesn't care if they're bonds, doesn't care if it's lone pairs. Electron geometry only matters on how many areas of electron density. Determine that first. Once you determine that, you can then draw it in that structure and see what does it look like in 3D space. So carbon will be tetrahedral. And I don't have any lone pairs. So this retains its tetrahedral shape for its molecular geometry. Reminder, electron geometry. How many areas of electron density do you have? Treat bonds, single, double, or triple. And lone pairs the same, meaning each one counts as one area. Each bond, so single bond, double bond, triple bond, is one area, and each lone pair is one area. And then you can determine your electron geometry and molecular geometry from there. What about H2O? H2O also has 8 valence electrons. You've got the oxygen in the center, bonded 2 hydrogens, and it's got 2 lone pairs on it. 1, 2, 3, 4. 4 areas of electron density. Which means tetrahedral electron geometry. Draw it out in that shape. Oxygen, hydrogen, hydrogen, lone pair, lone pair. Now, you can either leave them the same or you can erase the lone pairs. We don't actually need the lone pairs there. I don't really care. But you see, this is how I get this shape that we often draw water in. Because if I was to rotate this, it's that relative shape. This is called bent, and this is your molecular geometry. Remember, molecular, how is the molecule actually put together? But SCl2. So let's see. S is 6 valence electrons. Chlorine is 7. 2 chlorines, 14. We have 20 valence electrons. So S, Cl, Cl, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Normally I don't write them all out, but I don't have notes in front of me, so it's easier to make sure I'm using up all my electrons if I actually write it out. Looking at this, count up your areas of electron density around the atom you're looking at. By the way, we're looking at your central atom here. So 2, 4, 6, 8 electrons. 4 areas of electron density. I need to get my brain back on VSEPR and off of Lewis structures. So 4 areas of electron density. So tetrahedral electron geometry. Shrink this down to give us some room. Go ahead and redraw this in the shape tetrahedral. So I've got S, Cl, Cl, lone pair, lone pair. I notice this just looks just like water. S, Cl, Cl. Which we say is bent. So the molecular geometry of SCl2 is bent. What about SF4? Let's see, sulfur is 6, 4 fluorines, 28, 29, 30, 34 valence electrons. Sulfur, fluorine, 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 fluorine. That uses up 28. Or 32, I can't count, obviously. So let's count to make sure that I've got the right number now. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yeah, that sounds better. And 34. So I've got one lone pair on my central atom, my sulfur. And I've got 1, 2, 3, 4, 5 areas of electron density. Which means my electron geometry is called trigonal bipyramidal. I'm going to form a trigonal shape in the middle and then 2 pyramids, one on top, one on bottom. Go ahead and redraw that in your shape. Now remember, for trigonal pyramidal, that your lone pair will go on an equatorial position. Sometimes students recognize this sideways, sometimes they don't, so if you have to rotate it, this is your seesaw. So your molecular geometry is your seesaw. PCl5. So chlorine, 7 valence electrons times 5 is 35. Phosphorus is 5, so we have 40 valence electrons. Two, 4, 6, 8, 10, 12, 14, 16, 20, 22, 24, 26, 28, 30, 36, 28, and 40. I've used up all 40 of my electrons. I don't have any lone pairs to put on my central atom. I have 1, 2, 3, 4, 5 areas of electron density. That means my electron geometry is trigonal bipyramidal. And when I draw this into my molecular shape, my axial positions, I'll draw my equatorial positions in blue. This is also trigonal bipyramidal. So my electron and molecular geometry match because there's not any lone pairs. Remember, those will match when there's not lone pairs. And last but not least, XeF4. So 4 fluorine, that's 28, plus xenon is 8. So I can't count that fast. Sorry, I'm tired, you guys. 36 valence electrons. So Xe, F, 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 and F. That's used up 32 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Still have 34 and 36. So 1, 2, 3, 4, 5, 6. 6 areas of electron density. My electron geometry is called octahedral. I'm trying to write too low on my screen. I'm going to move this up a little bit just so I can write. And I'm going to shrink this because I'm already running out of space. So my electron geometry is called octahedral, but now I'm going to redraw this into my shape for octahedral. Actually, because this one's going to come with practice, because I've got 2 lone pairs, I'm going to draw my lone pair on the top and on the bottom. This doesn't actually matter. They're equivalent positions, but it's going to make it easier for me to recognize its molecular shape in just a sec. Should be a wedge up front and a dash going to the back. Another wedge up front and a dash going to the back. This is called my molecular geometry here. It's called square planar. Again, I'm forming a square right here. And although it's hard to see because I have the wedges and dashes, the wedges are coming out the board at me, the dashes are going into the board, so that's like the plane of the ground to us. It's actually a planar compound. Example, describe the molecular geometry of glycine. We have 4 interior atoms here. Nitrogen, carbon, carbon, oxygen. What are the molecular geometries of each piece? And the answers are over here, yes, but let's look at them. Let's look at nitrogen first. I've got 1, 2, 3, 4 areas of electron density. So it's based on a tetrahedral structure, but I have 3 bonds and 1 lone pair. That is called trigonal pyramidal. Carbon here, 1, 2, 3, 4. 4 areas of electron density and no lone pairs. This, tetrahedral. It's going to match its electron geometry since there's no lone pairs. Carbon in here, 1, 2, 3. 3 areas. Because that double bond counts as 1 area. This is going to be trigonal planar. It's trigonal because it's forming a triangle. That carbon itself, we can see here, is forming a triangular shape with the atoms 120 degrees apart. And oxygen, its favorite structure to form, 1, 2, 3, 4 areas of electron density, but 2 lone pairs. So 2 bonds, 2 lone pair, is bent. And which molecule has the smallest bond angles? Well, let's think about these structures. CO2, linear, 180 degrees. NH3, is based on tetrahedral, but it has a lone pair. It's called trigonal pyramidal. and the bond angle will be less than 109.5. SF6. Octahedral. And this structure, all the bond angles are 90 degrees from each other. And option D, BRF5. That's, let's see, 6 times 7, 42 electrons. So BR, that uses 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 6, 38, 40. That's what I thought. 42 electrons, so one lone pair. Put my lone pair up here. It's called square pyramidal. And due to that lone pair up there, these will be less than 90 degrees. So BF5 will be our answer. Excuse me. Go ahead and practice more more molecular structures, more VSEPR structures. The more practice you guys have, the better this will go.